Hi there. In this video, we'll look at how to find the derivative of an inverse trig function. And I've chosen as an example the arctan function. So we'll do this in two stages. First, we'll find a formula for the derivative. And second, we'll make sure that we express that formula in terms of x. All right, so here goes. Just to kind of lay out kind of a roadmap for what's going to happen here. We will need to understand, to complete this task, the nature of arctan as the inverse of the tan function. We'll need, along the way, the formula for the derivative of tan. We'll need a solid understanding of implicit differentiation, which is just an application of the chain rule. We'll need, as always, solid algebra skills. And ultimately, we'll need one of the trigonometric identities relating to the tangent function. So all these things will come into play in a lovely way. Let's get started. Okay, so the first thing to do is to convert this formula about arctan into a formula about tan. And the way to do that is just to recognize that we're given an input x, we're running it through the arctan function, and we're producing an output y. Let me just diagram that. Start with input x, run it through the arctan function, and produce an output called y. Well, can we run that process in reverse? Arctan is really the inverse function, so let's run it in reverse through the tangent function, the ordinary tangent function. Okay, well, if we start with y as an input and run it through the tangent function, we should produce x as an output. Okay, so everything I just said requires an understanding of inverse functions and inverse trig functions. There's another video on that if you need help with that. But with that, we can then write down, if I put y as an input and run it through the tan function, it produces output x, and we can write that down. Let me just clean up the screen, and then we'll go ahead and do that. All right, so start with input y, run it through the tan function, and you'll produce an output of x. Okay, these two statements right here are just mathematically equivalent. But the reason we do that is that the tangent function is something we know how to find the derivative of. So that will help us to find the derivative of arctan. Okay, so in terms of the roadmap, we've just used our knowledge of the nature of the arctan function as an inverse function. Now we've reached the point where we need to know how to do two things. Number one, find the derivative of the ordinary tan function, and number two, how to apply the chain rule. All right, so with that, we're going to compute the derivative now. So we need ddx of tan y and ddx of x. Okay. And in order to do that, let's stop off and revisit a couple of things. First of all, the derivative formula for just ordinary tan is listed here. And we'll assume for this video that you already know how to reach this particular result, that the rate of change of tan x is secant squared x. Okay, and the second thing that comes into play is knowledge of the chain rule. So let me just record a couple things here. We started out with y equals arctan x, and we also wrote that the tan of y equals x. Okay, and our goal is to find a formula for the slope of the arctan function. Okay, let me just diagram this out again. We're taking x, we're running it through the arctan formula, and we're producing output y. The second equation wants us to think of y as an input, run that through the tangent function, and produce an output of x. Okay, so what do we know about derivatives? Well, we know the formula for the derivative of tan something is secant squared something. Secant squared something. And in terms of the derivative of arctan, well, that's what we're trying to find. Okay, we don't know what that is, but we do have a symbol for that. We'll just represent that unknown using the symbol dy dx. Okay, and that is the slope of this guy. Okay, here's where the chain rule comes into play. The chain rule tells us that rates of change multiply, so we need to find the product of these two quantities right here and just multiply them together. All right, so let's go back and actually apply that. So everything that was just said amounts to, if you want ddx of tan y, you need, you need secant squared of y. Okay, just using words, the slope of the outside at the inside multiplied by the rate of change of the inside is a way to think of the chain rule. And this is what I just diagrammed out. We're just taking the product of these two rates of change. Okay. All right, so easy to write down, a little bit challenging to understand conceptually, but with practice it becomes second nature. All right, now for the easy part, the slope of x, or the derivative of x, is just 1. Yay. Okay, so with that, we've now used the formula for the derivative of tan x. We've used implicit differentiation, applying the chain rule. Now it's time to just simply do some algebra. And what we'll do is seek to isolate this quantity right here. We're trying to find dy dx in the first place. That's our goal. So let's go ahead and do that. And we accomplish that using division. So we get 1 divided by secant squared of y. Okay, and this completes the first task. If we just want a formula for the derivative, all right, if you're willing to plug in the y component of a given point, then you can just throw it into this formula right here and you will know the slope. And that's 100% legitimate. Okay, however, it's just nice to be able to express things. If we go back to the original formula, all right, if we think of x as an input to that formula, it's just nice to be able to express derivatives in terms of that input. Okay, so for that reason, we are going to now try to express that formula in terms of x specifically. Okay, can I clean this up for you? Let's see here. Doesn't want to let me delete that. Okay. So with that, we're now into sort of phase 2 of the project. And let me just make the comment that if you have good solid background knowledge, everything that happens over here to the left of this line is pretty straightforward. Okay, you could work that out with a pencil in about 20 seconds or 30 seconds. Okay, what comes after this requires some background knowledge from trigonometry. And so let's take a minute to revisit that. Okay, so this last step requires us to use some identities relating obviously to tan x. So let's take a look. Okay, and it's assumed in this video that you're familiar with this identity, but this picture is just showing a representation of the tangent and the secant in terms of a unit circle. If you apply the Pythagorean theorem, you get a squared plus b squared equals c squared, and that's why this is called a Pythagorean identity. Okay, so in terms of the problem we're trying to solve, all right, we were at a point where we had secant squared y in the denominator of fraction. And since this is a statement about numbers, we're free to write whatever variable we want. So in particular, I'm going to choose to write this not in terms of theta, but in terms of y. All right, still true. Okay, now what we'd like to do, okay, so reminder, let me go back to where we're coming from here. We have this formula. Can I highlight this for you? We have this formula, 1 divided by secant squared y, and we'd like to express that formula in terms of x. So let me just write the formula for dy dx is 1 divided by something, which we'd like to be in terms of x. So we're going to try to operate on secant squared y in such a way that it ends up as a formula about x. All right. So with that, I think we can do this. Let's go back to one of our earlier statements that when we run y through the tangent function, we produce x. And so this is kind of like our decoding scheme for telling us how to take y statements and make them x statements. So with that, I noticed that tan y is a part of this, and yet it's really tan squared y. So let me just square both sides here. Square on the left side, square on the right side. And now you can see, let me clean this up.
Activity buses are here.
Oops.
Please make your way to the main entrance. They will be leaving very shortly. Again, activity buses are here. Please come to the main entrance.
Okay, we've got activity buses at Sherwood today. Great. All right, so if we square both sides, we get that tan squared is x squared. So what I'm going to do now is take tan squared out and replace it with x squared. Okay, we're just going to perform a simple substitution. All right, so 1 squared is 1. Tan squared y is going to become x squared, taking tan y out and putting x in, and that is equal to secant squared y. All right, so I'm going to go back to my page, and where I see this expression, I'm going to substitute this expression, 1 plus x squared. All right, here goes. So in place of secant squared, we can write 1 plus x squared. Okay, and what we've done right there is we've reached the goal of expressing the formula for the derivative as a function of x, and that was our major aim. Okay, so this right here, in summary, is a formula for the derivative of the arctan function. So d dx of arctan x can be found using the formula that we just derived. Okay, I truly hope that this helps you to understand how to find derivatives for inverse trig functions. Let me just make the comment that good practice and exercises would be to take another inverse trig function like arcsine, arccosine, arccotan, arcsecant, arccosecant, and derive the formulas for those. Just a heads up about how those problems would differ from the one that was presented here. Let me just go back to how this looked originally. So the nature of inverse processes will come up in all of them. All right. In terms of which specific derivative, well, if you're on some other function other than tan, you would need that particular derivative formula. Always this is going to happen, and using the chain rule, always you need your algebra skills. Each problem involves its own identity. It just might not be the identity, obviously, that relates to tan. It might be some other identity. However, I will tell you that all of the identities that are needed are Pythagorean identities, so if you know those by heart, you should be good to go. Hope this helps. See you next time.